Good evening, students. So, we'll continue discussion on the continuous system. We have we have formulated the equation of motion for the case of simple case of Euler-Bernoulli beam case, and now today, after equation of motion, we formulated the eigenvalue problem, which was differential equation, ordinary differential equation for beam case. So today I will start with the more general formulation, and some definitions I will introduce, which will be helpful for different kind of elements like beam or torsion case or cables, or even for the two-dimensional problems. So whatever initially half of the lecture I'll be introducing the general formulation of the eigenvalue problem, characteristics of that, orthogonality property, and that kind of thing. And then we'll see that we'll take up a cable or the string problem. We'll formulate the equation of motion for that. For beam case, because the differential equation is more complex, we'll take up that in the maybe after 2 or 3 lectures. Initially, we'll be taking more simpler case of the cables and torsion of rod or axial vibration of rods. So I'll share this the PPT. So last time I formulated the eigenvalue problem and even the boundary conditions I described for the beam. I will leave it that particular formulation at that stage, and we'll move based on that background on the more general formulation. So here earlier we defined the eigenvalue problem. And the eigenvalue problem I will just show once. This was the eigenvalue problem which we defined. That was ordinary differential equation, but fourth order differential equation, in which this was the elasticity, elastic force, and this was the inertia force. So now let us say we have one linear homogeneous differential equation which is function of W. So I'm defining a this kind of general expression in which A1, A2, A3, A4, A5, these are some kind of coefficients to the derivatives of these terms. These coefficients can be function of the spatial coordinate. That means depending upon the dimensions, we can have, they can be function of x or xy or xyz. So depending upon the problem, these coefficients can be function of spatial coordinates. And correspondingly here, because here only the derivative with respect to x and y is there, so this is specifically for the two-dimensional problem. So these various differentials are there. Even we can go for higher order differentiations. But here we are representing the whole, the right hand part as L operator within bracket W. Because here W is common, this homogeneous equation W is common, and this L operator is a linear differential operator. So if we remove the W from the right side, the L operator can be expressed in this form. So if we are saying we are applying the L operator to W, then these derivatives will come. So this is a general two-dimensional a linear differential operator L. Or linear operator, that means if we have, let us say, within the bracket C1W1 plus C2W2. So if this is equal to, because C1 is C1 and C2 is constant, so we'll be having C1 LW1 plus C2 LW2. So here understanding is there that L operator is this. So or similar to this, W1 will be applied this L operator and also W2. So here you can see it is something like once we are opening the bracket and it is applied to each of the function W1 and W2. So this is linear operator. Sometimes this operator may not be nonlinear, so we are not talking about that. We are talking about only the linear operators. So now I define one operator, a general operator. So let us go back to our eigenvalue problem which we had earlier for the beam problem. So here we have differentiation with respect to x here twice, then this property of the beam, and then again differentiation yx is there. So here w is nothing but capital Yx, y function of x. So I'm trying to write this particular eigenvalue problem in a more general way here. I'm saying L operator. The L operator for this problem may be different. We'll see what will be the L operator for this. L or W, which L is applied to W, and then lambda M operator. This is also another differential operator, and which is applied to the W. So if we compare these two equations, you can see or let us take the L operator. L operator is a, if we remove the Y, then we'll get the L operator. So that will be a fourth order differentiation L operator. This is a one-dimensional problem, so derivative with respect to Y and other things are not there. So L operator will be here, left hand side without Y, because here Y or W is Y. Okay, so now we are saying that this is a general eigenvalue problem for form, which is for beam case is this. So here the various let us say property of this operators we see. So L operator and M operators are linear homogeneous differential operator. The L operator is having order of derivative is equal to 2p. That is very important to understand. The L operator is having derivative order 2p, and the M operator is having derivative 2q. And in general, we will find that p will be greater than q. So here and the boundary conditions. Okay, we'll discuss more about this general eigenvalue problem, but because we have associated boundary condition, one of the boundary condition, the shear force boundary condition was this, one of them, because we had the bending moment boundary condition, then the slope boundary condition, and displacement boundary condition. So just for example, I've taken one boundary condition, which is shear force equal to 0 at x is equal to 0 for cantilever beam case, let us say. So that particular thing is the boundary condition. Now I'm defining a more general boundary condition in which the right side we can have some terms. So that means I'm saying BI operator, this is also differential operator applied to W is equal to lambda. CI is another operator here, this is not constant, which is applied to W. So the more general boundary condition is this one, in which we can have both sides operators bi and ci, and even we can have this lambda eigenvalue on the boundary condition. So this is the most general boundary conditions we can have, and this boundary conditions will be p number. P number, what is p? P we have defined that that is nothing but the L operator order of differentiation is 2p. So half of that is p. So at each boundary, we'll be having p number of boundary conditions. And at each boundary, we need to apply. So like at x is equal to L, we'll be having two boundary, p number of boundary conditions. Similarly, at x is equal to 0 also, we'll be having p number of boundary conditions. For a specific case, I will describe these numbers, like for beam case or other case, I will describe this more explicitly. So here the BIW and CIW are linear differential operator involving derivatives of normal to the boundary and along the boundary. So if we have, let us say, two-dimensional problem, the boundary can be like if we are talking about circular plate, then we'll be having boundary curved, boundary will be there. So these boundary conditions can involve derivative normal to the boundary and along the boundary of the domain. So here I'm talking about more general boundary conditions formulation. And here the BI or CI will be having maximum derivative order, that will be 2p minus 1. So L operator is having order of differentiation 2p, but boundary conditions will be having one less order of differentiation as compared to the eigenvalue problem. This one, the eigenvalue problem M and L I defined, where M can be differential operator. But in this particular case, we see that on the right side, there is no differentiation of the y. So this is a simpler case. So that case, we can able to define in a special case the eigenvalue problem like this, in which we have L operator applied to W, lambda, M operator, and W. So M operator is here mx for the beam case. W is anyway capital YX. So this is a special case of eigenvalue problem in which M operator is only a function, because M can be function of X. So this is a function only. It's no, or it can be constant, but it's not differential operator. And most of the case, we'll see that our eigenvalue problem will fall for the beam case and other case in this particular special. Okay. I think someone has to mute. Okay. Okay, so I think some trouble. So here, this is a special boundary condition. The eigenvalue problem, which will fall under this beam problem or other string problem I was talking about. And this is simpler to handle as compared to, and even the boundary conditions, if you see in our case or the beam case, there is no right side. So that particular boundary conditions can fall under special category in which BI operator is there, CI is 0. And this kind of boundary conditions are easier to apply as compared to the more general this boundary condition. So this eigenvalue problem associated with this boundary condition is the most general boundary condition representation. But this one associated with the boundary condition this will be having a simpler solution. And so if boundary condition is in the boundary condition itself, eigenvalue is present, then the solution is more difficult. We'll see some of the case of this kind also, but maybe after 2-3 lectures, that kind of case we'll consider. Here, this W is if you want to solve the eigenvalue problem of this kind, W is the eigenfunction. Lambda is eigenvalue. So often, as I mentioned, the solution of this eigenvalue problem becomes difficult, especially if boundary conditions are complex or the geometry of the beam or that kind of thing is complex. So often we not get the exact solution of this. So in the next chapter, we'll be talking about approximate method in which we will compromise on this solution in the form of maybe satisfying the equation of motion or satisfying the boundary conditions. So these are the some three type of definitions of the functions we can choose from. That is for approximate solution. So one is the admissible function. So admissible function is the function which satisfies the geometrical boundary condition of the problem, and it is this is a function of spatial coordinate. So it should be differentiable p times over the domain of that particular element. So this is the simplest function we can think of, which will satisfy our requirement to get the eigenvalue. Comparison function is having a little bit more requirement, so it satisfies both the boundary condition, geometrical and the natural. So last class I explained geometrical boundary conditions, like for beam case, is the displacement or the slope is 0, and natural boundary conditions are when the shear force and the bending moments are 0. So if we satisfy all the boundary condition and the functions which we have chosen, this that is 2p times differentiation. We should be able to differentiate without vanishing that function. Then that is called comparison function. Eigenfunction is the exact solution. So that is something like mode shape. So, and the eigenfunction satisfies all the boundary condition, and the differential equation in totality, it satisfies the eigenvalue problem or differential equation. So in this chapter, we will be aiming for the eigenfunction, which is the closed form or the exact solution of the differential equation, eigenvalue problem. But in the subsequent chapter, we'll go for the comparison function or the admissible function, because for more complex geometry or boundary condition, they are difficult to solve. Some of the property of this eigenvalue problem operators L and M now we'll define. If you go back to the discrete system, we define the mass matrix and the stiffness matrix as symmetric, and that was having some effect on the eigenvalue, because when the mass matrix and stiffness matrix are symmetric, eigenvalues are real and they are positive, and so that we get the real natural frequency. So here also the L operator and M operators are having some property which is called self-adjoint. It's similar to the symmetry nature of the discrete system. So self-adjoint property, we can define, let us say if we have two functions, u and v are two functions are there, they are comparison functions. So if we have the u L operator v integrated over domain is equal to, we have swapped the function. So v L operator u b. So this is the L operator will be self-adjoint if we are able to satisfy this condition. So you can see u, v, and then vu. So, and similarly for M operator. For M operator also, if we apply the u multiplied by the M operator, this is applied to v and integrated over domain. If it is equal to, if we swap the function, so then the M operator also will be self-adjoint. So the symmetric nature which was there in the matrix. So here, once this these operators are self-adjoint, then we'll be getting the eigenvalues real, and those things will be valid here. And the positive, as we define for the matrices, the positive definite and that kind of definition. So for L and M operator also, same thing is defined. So if we have comparison function u, and if the operator L is satisfying this condition, so you can see here both are u L operator u integrated over domain. If it is greater than or equal to 0, then we can able to say is positive. If L, this operator, we can able to say positive definite only if this integral is 0 when u is 0. That means when there is no displacement is taking place, is positive definite. If this integral can be 0 when u is not 0, then this operator will be only positive. So here I mentioned if L is only positive and M is positive definite. Generally, M is similar to the mass matrix. So we have seen that the mass matrix is related with the kinetic energy, which is always positive definite. So here also M operator will be always positive definite. L operator, which is related with the elasticity, this can be positive or positive definite depending upon this particular definition. So if both L and M are positive definite, then the eigenvalue problem will be called as positive definite. If L is positive but M is positive definite, then this will be called semi-definite system. For positive definite system, all the eigenvalue are positive, as we had in the case of discrete system. For semi-definite system, where L is only positive, we will be having at least one of the eigenvalue equal to 0. And that will belong to the rigid body mode. And this property, the positiveness and the self-adjointness, we can able to check by doing the integration by part. So when we'll go for the specific case of the string problem or cable problem or beam problem, when we solve, we'll check this condition, the positiveness and the self-adjointness. And because here L operator is very general, so here it will be difficult to do integration by part because we don't have the actual form of the L. So once we have actual form of the L, we can able to do and check this. But here, this particular, if you see that the integration is written D. So that means it is applied to not only the one-dimensional problem, but is applied to the two-dimensional problem or three-dimensional problem. So if we have two-dimensional problem, that this will be double integral. and here we'll be having dx and dy. Similarly, for three-dimensional problem, it will be triple integral. Okay, so now we'll look back with respect to the beam case, whatever the property I defined. So this is the eigenvalue problem for the beam we obtained in the last class, and this is the eigenvalue problem, special eigenvalue problem where the M operator is not differential operator I defined today, but L operator is a differential operator. So if we compare these two equations, we'll see that the L operator is fourth order differential equation or differentiation where y, x we have removed. M operator is only function of x, it's not a differential operator. Now we have seen that the L operator was having 2p order of differentiation. So for beam case, 2p is equal to 4 because L operator is having order of differentiation 4. So 2p is equal to 4, and the 2q, which is the order of differentiation of the M operator. So here the M operator is having no differentiation, so that is equal to 0. So from this we can get P is equal to 2 and Q is equal to 0. So now coming to the boundary conditions. So the earlier I defined the 4 type of boundary condition which was possible. So let us say the case of the cantilever beam in which this end is fixed. So we have x is equal to 0, displacement is 0, and the slope is 0. And at the free end, we had the bending moment equal to 0 and the shear force equal to 0. So these are the 4 possible boundary conditions. First 2 are geometrical boundary condition, and the last 2 are the natural boundary condition. Now if you compare that with the boundary condition, general boundary condition, but special one in which we do not have the CI operator in the right side, and the eigenvalue is also not there. So if we compare this, so this is the boundary condition for each boundary. So what are the boundaries here? We have one boundary at x is equal to 0. We have another boundary at x is equal to L. So we have 2 boundaries, and at each boundary, how many boundary conditions we have? So according to that, we should have p number of boundary condition at each boundary. What is p? P is 2 for the beam case. So that means here we should have 2 boundary conditions. So you can see we have at x is equal to 0, we have 2 boundary conditions. Similarly, at the free end, we should have 2 boundary conditions because p is equal to 2. So these are the 2 boundary conditions we need to have for beam case, 2 boundary condition. We'll see that for other kind of problems in which when we talk about the cable vibrations or the torsion of rod, and then these conditions will be different. The P will be 1 at that point of time. So for those cases, only the one boundary condition need to be satisfied at each boundary. But here we have P is equal to 2, so at each boundary we have 2 boundary condition. Now, as we have defined this, so let us concentrate at the x is equal to 0. So x is equal to 0, what is the B operator here? If you compare this and the first equation, because there is no differentiation, so directly here B1 is equal to 1, because the coefficient of this is nothing is there, so B1 is equal to 1. Here this is B2 because I is equal to 1 to P is 2. So for I is equal to 1, we have already written B1. For I is equal to 2, B2 will be this differentiation, d by dx. So at x is equal to 0, we have this boundary condition where B1 is 1, B2 is single derivative. Now at x is equal to L at other boundary. At other boundary, we have these two boundary conditions. So here, this will be B1. So B1 is what? B1 is the second order differentiation. B2 is what? This should be B2. This should be B2. And this should be ordinary differential equation. Similarly, this is also should be ordinary differential equation because we already converted the, yeah. So here, so B1 is this. So EI double derivative with respect to this also should be ordinary differential equation. Similarly, this here, this is a third order differentiation. Now, if you see in the whole this boundary condition, what is the highest order of differentiation? So highest order of differentiation is there in the shear force, which is 3. The derivative is 3. And I already mentioned earlier, the B operator should have differentiation at the most 2 minus P or 2P minus 1. So 2P is 4 minus 1, 3. So this is satisfying that condition also, that the order of differentiation and maximum order of differentiation in the boundary condition can have one less than the eigenvalue problem. So, and here that condition is also, we are satisfying that at each boundary we should have p number of boundary conditions. So at here we have 2 boundary conditions, and here also we have 2 boundary conditions because p is 2 for the present case. So this is the comparison or correlation between the whatever the eigenvalue problem, general eigenvalue problem we define, associated boundary condition, how we can able to correlate with the a particular case of beam. Okay, so now we'll see some of the more property of the general formulation of the eigenvalue problem. So this is a special kind of boundary condition in which eigenvalue problem in which M operator is not a differential operator, and the boundary condition is not containing the eigenvalue. So this is, as I mentioned, is simpler. These equations are homogeneous, ordinary differential equation. So solution of this will be that this lambda, which is eigenvalue, will be having a sequence of eigenvalues. So it should be infinite. So because this is a continuous system, so we should have n is equal to infinity. So we'll get a sequence of eigenvalues and corresponding eigenfunctions W1, W2, W infinity we will get. So as we had in the discrete system, we had the eigenvalue and the eigenvector, but there only the n number of eigenvalues were there. But here we expect the eigenvalues will be infinite, and corresponding eigenfunction, which is nothing but the mode shape, will be also infinite in numbers. The amplitude of these eigenfunctions again will be arbitrary, but the shape of the eigenfunction will be unique. So if it is, let us say, sine function is there, so shape is defined, okay, this is sine, but if some amplitude is attached with that, so that amplitude will be arbitrary because we have seen that we don't get the unique amplitude of the mode shape, only we get the relative mode shape in the eigenvalue problem. Okay, and this is a special case when we have 2 eigenvalues which are same value. Then those eigenfunction combinations can be can also be eigenfunction. So this is a very specific case. Now we'll see the orthogonality condition which we had for the discrete system. Similar thing, we'll prove it here for the continuous system. So let us say we have the two eigenvalues of the system. So let us say we have solved the eigenvalue problem, general eigenvalue problem. We got the eigenvalues and eigenfunction. So we picked up for such eigenvalue problem which was self-adjoint. That means we had all the eigenvalues real and positive. So we picked up the rth and the sth eigenvalues, two arbitrary eigenvalues we picked up, which are distinct eigenvalue. Corresponding eigenfunctions are WR and WS. They are corresponding. So lambda R is related with the WR and lambda S is related to the WS. So we call it as a rth mode eigenvalue and eigenfunction. This is sth mode eigenvalue and eigenfunction. Because they are the solution of the eigenvalue problem. So if we substitute this in the eigenvalue problem, we should be able to satisfy this. So this is for the rth eigenvalue we have substituted. It should satisfy the equation because WR and WS are the exact eigenfunctions which has been obtained from the eigenvalue problem. So this is for the rth and this is for the sth eigenvalue and the eigenfunction. So now we will multiply this particular first equation with the WS, the other eigenvalue eigenfunction, and the second one equation, both the sides will be multiplying by the WR, and then we'll integrate this over the domain. Domain means over the length of the beam or over the area of the plate or like that. So you can see we multiplied this both this by this, and then we are subtracting one from another. So if we multiply this by WR, WS, throughout, integrate it, subtract the first term of this, and first term of this is in the left side. So WS, LWR, this one, minus, because we subtracted this, so WR into LWS, So this is the integration. This is the of the left side. Right side also, we have WR. So here lambda R, WS, MWR minus, then we multiply by this WR like this. Because we are subtracted, so these two equations became one. Now we'll see this self-adjointness property, what it says. So if was WR and WS is self-adjoint, then as we have seen that earlier we took the V and U and V. Now we have WS and WR. So if the operator L is self-adjoint, even if we swap this to WR and WS, that should be equal. So that is the self-adjoint property. So of the L operator. Same thing we can have for the M operator. So WS, WR, if we swap this, then also it should be equal. So this is the self-adjointness property. If we go back in the previous slide, we'll see that this quantity and this quantity here, this swapping of the eigenfunctions are there and same operator. So basically they're equal. So this and this will get cancelled. So left hand side will be 0 using the self-adjointness property of the L operator. So, and here this quantity will be equal to this because lambda R and lambda S are constant. So we can take common. This will not cancel everything, but we can able to take common these two because they are equal. So here we have done that. So lambda R minus lambda S, and we have taken the mass operator outside. We have taken one of them, WR and WS here. We could have taken other way around also, but because they are same, so I have taken WR and WS. Now here, because we took the two eigenvalues which were distinct, so in general they are distinct, so they cannot be zero. If they cannot be zero, so this equation will satisfy only when this integral is zero. So if we equate this integral equal to zero, so that is nothing but the orthogonality of the eigenfunction with respect to the M operator. So WR M operator applied to WS integrated over domain is equal to zero because they are two different eigenfunctions. So they are orthogonal to each other. So they are zero. So here we can able to say that WR and WS are orthogonal in generalized sense. Now, if you see this equation, if this equation we go back to the previous slide. So here, because this is zero, according to the orthogonality condition. So that means here we'll be having same thing zero. So like here, if we are multiplied by this by WS and integrate over the domain, and this quantity will be zero. So we'll be having L operator with different eigenfunctions also will be zero. So not only the M operator, but also the L operator also will give the same condition, the orthogonality condition of the eigenfunction. So these are the two property which we'll be using it. If you remember in the previous discrete system, when we had the mass matrix or the stiffness matrix, if we had two different eigenvalues, eigenvectors, then they were zero. So either it is a stiffness matrix or either in the mass matrix, it was same. So, but here in continuous system, we have M operator and the L operator, but the overall concept is same. And so this is the orthogonality condition. Now we'll go for the normalization one. So when we normalize the eigenfunction, then we generally normalize with respect to the M operator, which is equivalent to the mass matrix. In the discrete system, we normalize the eigenvector with respect to the mass matrix. So same thing here also we are doing it. We are normalizing with respect to the mass M operator. Here now you can see they both are WR. So when the both are having same eigenfunction, then we are equating to 1, where R can have infinite eigenfunctions. So we are normalized like this. Now, if you see this normalization, if you are doing it, and the orthogonality conditions, this one, we can able to combine in one equation like this. So this is a Kronecker delta function, which will be 0 if R is not equal to S. So that will give us the orthogonality condition. If R is equal to S, then we are getting the normalization equation. So this is the this is giving us not only the orthogonality condition. When R is not equal to S, then it will be 0. If both are same, then that is the normalization we have generally do. So once we have the eigenfunction in the normalized form, like this form, then this eigenfunction which we were talking about in the previous slide, they are orthogonal to each other. And now we'll say they are orthonormal to each other because they have been normalized. So they are representing the same thing, but only thing here, once we are saying orthonormal, they have been normalized also with respect to mass. Okay. Now the next thing is we had in the expansion theorem the discrete system, where we mentioned that the any particular response can be expressed in terms of the eigenvector multiplied by some constant. So same thing is here we are writing. So these are the eigenfunction multiplied by some constant c, and we are summing them from r is equal to 1 to infinity to get the, so any function if you want to represent which will be basically a known displacement of a particular system can be expressed in terms of their in terms of their uh, eigenfunction multiplied by some constant. This constant will depend upon the initial condition of the problem, and this can be expressed like this. I will explain how this can be obtained. Basically, if we multiply this equation, let us say with m here I have mentioned, if I multiply this by MWR, M operator WR, and integrate over domain both sides. So here also I have multiplied by the M operator WR and integrated over domain. Now in the right side, if you see, because this is summation, terms are there from r is equal to 1 to infinity, and here we have WR only. So all terms from 1 to r minus 1 will be 0 according to the orthogonality condition, or even r plus 1 to infinity, there will be 0 according to the orthogonality condition, because once the I is not equal to r, there will be 0 according to the this. So only term which will be left out will be uh, that will be the WR. Here WR will be left out and CR. Now WR, MW, and operator WR is nothing but 1, because we have normalized the WR with respect to the mass matrix. So that will be 1. So only the CR will be left out here. So CR is this quantity which is expressed here, same thing. So here the function W satisfies the homogeneous boundary condition of this. So if W we have chosen such that it is satisfying the boundary conditions of the problem, and if we take the L operator on the W, if it is continuous, it is not vanishing, then basically we can able to write the W in terms of this eigenfunction. So this is called expansion theorem, and we'll be using this for sometimes for finding the solution. Sometimes when we are going for the approximate solution, then this infinite terms will be truncating into some n numbers, because taking infinite terms will be impractical in some cases. So we will be taking some truncated value of this. Okay. So this is the expansion theorem, which we'll be using for modal analysis, as I explained in the previous discrete system also. So after this, I think I'll take up one simpler the string or the cable. Okay, so here I'll just stop for a while if you have questions, and then I think I can take up this in the next class. So the cables, you must have seen there are various applications of this. One of them is the bridges. Now people are constructing with the this kind of cables. So these cables are preloaded. So they are having preloads, and because of that, they can take the weight of the bridge. And but when the vehicle passes through this kind of bridges, then the vibrations of the bridge take place, and this cable are the reasons for that vibration, because they are flexible. So we'll analyze such element, which is the most simpler for the continuous case. because beam is having, we got the fourth order differential equation, but for this case we'll be getting the second order differential equation. So maybe I'll take up this in the next class. So if you have any questions till now, you can ask. Yeah, Bharat.
Sir, my doubt is not regarding the topic. Regarding assignment, I have a doubt, sir.
So why don't you email? Because that is the most convenient way. Okay,
not
just
not regarding the solution how to do, sir. Like for assignment 4, I have solved the questions which have got the equation of motion in assignment 2. But today my assignment got returned saying that 2 of the questions are wrong. So like it is difficult to do again like those 2 questions for the new equation of motion. For this assignment itself, can I submit the assignment for which have from the equations which I have got?
The best is you update it. No, updating will not take much time. Okay, because as I mentioned, we had some difficulty in the checking in the assignment because our students, PhD students, were away. Now they have come, so now they are trying their best. So if you got some positive response, you update it. What is there? Updating will not take time. Got it?
So, like I have failed that thing now again I have to.
Yeah.
Like how do you know like can we get that original answers so that we'll submit
The
the new thing?
answer is not important. Main thing is whether you understood the concept clearly or not. Okay, because several students are asking questions. I'm replying them after 2-3 iterations, or their concepts are clear. No, don't ask the final answer. No, because I've given some problem, put mind on that, and then if you have queries, you're always welcome. I never said you don't ask a question through email, because through email you can send your part of the formulation snapshot. You can send me. I don't think I reply after 1 day or 2 days. Quickly I reply those things. Okay.
Yes, sure.
So redo it. It will not take time. Definitely, it will not take much time.
Okay.
Okay.
Hello.
Yes, sir.
Yeah.
Hello.
How is this?
Uh,
Please
sir.
raise your hand.
Okay.
Rakesh Dangal.
Yes, sir. Sir. Means I also have submitted the assignment too, but I realized that I have made some mistake while solving the problems. So can I resubmit it, sir?
Yes,
Like
yes. You request me for returning. I will return it and you submit. No, because here main thing is you should able to understand those 3 problems completely. If you can understand 3 problems completely, right up to the approximate method, the purpose is solved.
okay, sir.
Okay, it's not the punishment or the giving marks. Is the understanding is the main. Because you are away, so unless you solve with confidence those 3 problems, I think the purpose is not served. Understanding of the subject will be clear if you can able to solve those 3 problems. For discrete system, for continuous system, again I will give 2 more problems. So total 5 problems are there only.
Okay, sir. I will drop them.
Yeah. So throughout the semester, only 5 problems you are solving basically. 3 for discrete and 2 for continuous. But
Okay.
yeah, no, but different methods, but same problem, so that you're thorough in that.
Okay, sir.
Yeah. But I'll encourage you can take your friend's problem also, solve them also for practicing. But three is and plus 2 will be mandatory. Okay.
Okay.
Yeah. Any other issue? If you have any issue, please email me also. No, because always it's not. Yeah, Nikhil.
Sir, in assignment 2, sir, I have submitted the solution of 2 questions, but one question at that time I haven't submit. But now I am able to solve that problem. Sir, can I submit now?
Yes, yes.
Only third problem.
Yes, yes. You can submit.
So
No,
for
that is
that
good.
I have to mail you or.
Yes, yes. I think now you'll get returning. They'll check and return, no? So then you can
Yes,
submit.
sir.
Yeah.
Okay.
Because gradually they are checking it. I think by tomorrow, I think they can check all of them.
Okay. Thank you.
Okay. So I think on Saturday we have quiz. I'm just announcing again. Yeah, usual time during the class hour. I think that is Tuesday timetable. So 5 to 6 we have the quiz. Okay, then bye.